Test. Okay, better. Okay, well, thank you for inviting me. I decided to do a bit of an unusual talk today, and it's a bit of a challenge to present the GNUnet, because it's our attempt of rebuilding the Internet. And if you've ever seen a talk on the Internet, it was probably a bit shallow, so expect this one to be a bit shallow as well. So what's the motivation? Well, the basic motivation is we look at the Internet, it learns too much. It's not appropriate for a civil network these days to have an Internet as it is designed. As we all know, when we designed the Internet as a society, well, DARPA had a certain set of requirements for us, like do not use encryption because that's a national secret. And as a result, the IP protocol leaks information like crazy. You know, the IP header from where the packet goes, where it goes to, which port it goes to, that's just the beginning. The result over the last 30, 40 years of what we have built is a system that is having lots of insecure defaults still and has rather high complexity for management. Most importantly, it also has a lot of centralized components. We have IANA that allocates IP address space. We have ICANN and the root zone that have to be managed centrally. We have a bunch of certificate authorities that we use as our trust anchors. And all of these are, of course, being actively compromised, let's say, by the respective state attackers. The other problem, there's two problems with these things. There's, first of all, you have the administrators themselves that might be malicious or incompetent, and then they become targets. So if you have somebody who operates your network infrastructure for you, he himself will become a target. So we've seen this with the Snowden revelations on Stellar, where the network administrators of Stellar, that's a satellite network provider for Africa, were personally targeted because, hey, they had access to this critical infrastructure that could be used to turn off internet access, reroute packets for people. So the moment where you are an administrator, you are also a target. It's not just that you're powerful, you're also a target. So not having administrators would actually be very beneficial for us as a society, because we can then effectively say, well, we are in charge, each of us for ourselves, and we don't have to kind of say, oh, well, I have to depend on this other person to set me up, to hook me up, to control me, to block my access, enable my access, whichever. So I don't like administrators. So I'm trying to build self-organizing systems, or peer-to-peer systems where effectively it's flat, there's no hierarchy, nobody is in charge, but it still kind of works. At least that's the goal. Does it not work? Used to work just a second ago. Okay. So here's the Internet for you, somewhat simplified. We have the usual physical layer, Ethernet, IP, BGP, TCP, UDP, DNS, and then Google on top of it. I understand this is a slight simplification. The IETF has now revised the stack. As you know, we have a layered design for the Internet. So we have above TCP, we have TLS, and above TLS we have DNS, and then we have TLS above DNS. That's a bit more interesting these days. So that's why I'm saying it's a simplified version. Biggest problem replacing Internet is we can't really afford to replace the physical layer. You know, if I propose that, let's build that one new, everybody would laugh, right? So we have to kind of start with what is there as a communication infrastructure. So we just say, okay, we have HTTPS, we have TCP, we have WLAN, we have Bluetooth. Whatever already exists to communicate between two peers, we treat as, yeah, we can use this, but this is not reliable, not secure, out of order, possibly. You know, people can listen in. We don't assume anything there in terms of strong semantics from a security point of view. And it, may not be that anybody can talk to anybody. Like this Internet idea was every computer can talk to every other computer. No, we assume it might just be a local area network, an ad hoc wireless network, whatever. Right? So just, there's some physical way to communicate that's terribly insecure and has terrible semantics. Above this, the first thing we do is we run effectively OTR. So with the Ethernet these days, of course, there's no encryption. Everybody can fake a MAC address. Everybody can spoof a MAC address. Everybody can listen in. We first run OTR on that layer just to be done with, basic programs like Tempora. Then we do decentralized routing on top of that, so a distributed hash table. There are a bunch of ideas. We have currently the R5N DHT. I've been talking to people last week saying, oh, I've got even something better. I say, well, show me that it's better, and we replace it. But you have a routing algorithm that is decentralized. Then we do end-to-end encryption, of course, again. So this is effectively axolotl providing an SCTP-like interface. For those who don't know SCTP, think TCP or UDP and all of these variants combined. Then we have an alternative public key infrastructure called the GNU name system. On top of this, we build applications, and that's then roughly the GNUnet at the same level of simplification. So what I wanted to do today is effectively give you a fast tour de force through the various GNUnet features. And the motivation for me was, if you want to try to build systems or try to build a better internet, I want to give you an idea of what we have as a starting point. And you may say, well, that's not for me. I'm not building systems. I like to attack systems. Okay, well, you can also maybe try to attack it. That's fine too. But if you want to know what is all there, what are the various components that are there, I want to give you an overview. And because I'm only having 45 minutes and not 45 days or something like that, or 45 hours at least, and usually presenting one of those in depth takes about half an hour to an hour, I decided what I'm just going to do is tell you what they do, not how. So it's a bit unfair, right? From a research point of view, you also want to know how does this work? And the answer is in most cases, well, read the paper. Okay. So let's start with the lowest layer, which is kind of shared for everything. That's our abstraction for the system interface. And I'm very much looking forward to a working Etheros that is universally available and has all of the basic features we would need to build a system, because then I can simplify that dramatically. So here we're trying to both work around the atrocities in the C language and the atrocities in the operating system interface and making it work on FreeBSD, Linux, and Windows and nightmares, right? So, it's not great to have to do it this way, and it's awful complexity you wouldn't want to have. That's why I'm looking very much forward to Etheros solving all of those problems for us. But for now, you can just run it on a standard system thanks to a little utility library. Then, as the other foundation, we have, of course, a couple of cryptographic primitives. You find the usual things, so number generation, symmetric encryption, hashing, elliptic curves, signatures, homomorphic encryption, blind signatures, so, some of the features you might commonly see in slightly more advanced network protocols. Now, that's the foundation. Then, one of the key things we wanted to make sure is that we effectively got good compartmentalization. So we have lots of code, and we want to isolate the bugs. So if you have a problem in one layer, you don't want it to affect the other parts. And a lot of the code is written in C, some code is written in Java, some code might be written soon in Rust. And so we want to have different languages, we want to be able to mix them. So we run all of the different subsystems as a separate process, which means we can set for each process different policies for the operating system, so AppArmor profiles that say, this process doesn't need to write to disk, so it should never do so. This process doesn't need to communicate with the network, so it should never do so. And so even if in this individual process you have a particular bug, the policies that you can set for the process can restrict what it can do, how badly it could impact things. Not to mention, of course, if you try to understand how the system works, you can look at each individual process, audit them individually, and not have to worry about how do they interact, because they have a well-defined inter-process communication interface to interact with each other. So the result is effectively, if you run a GNUnet peer these days, you're running like 50 processes. Now, running 50 processes, starting them by hand in the right order is a bit messy. So you have kind of a master process, that's the ARM process, named after a subsystem that IBM had in their OS 360, which is like systemd, and that starts all of the other processes when they are needed. Right, so it's kind of like a hypervisor process. So what you need to know here is if you want to start the system, you use GNUnet ARM -S and -E to stop it, because you don't want to start each of these services individually. And then the services among themselves communicate via effectively remote procedure calls, typically on Unix domain sockets if you're on a Unix system. Okay. The lowest level service that we have is the transport service. Here we effectively say, okay, we need to establish these communications with other peers, and we don't know what is below. Right? Below could be TCP, could be UDP, could be an IPv4, IPv6 address, could be HTTP, could be HTTPS, could be WLAN, could be Bluetooth, whatever. All right, so you have a pluggable architecture, and the semantics that the transport effectively is supposed to provide is unreliable, unencrypted, out of order, best effort kind of semantics, what you would expect from Ethernet equivalents. The service has a couple of additional functions, like it's supposed to enforce quotas. So if your user says, don't use more bandwidth than this, we can enforce that there. We do stuff like NAT traversal. We can just say, I only want to be visible to certain friends. So I don't know if you know the situation in Russia for a couple of years. It has been effectively illegal to participate in these kind of networks. So you really want to make sure that your peer doesn't quite appear on the network as I'm participating. So you can say, well, only establish connections to other friends. Maybe I'm running as an HTTPS reverse proxy, so I'm behind the website, and everything that comes to me looks like it's website traffic. So there might be some ways to hide your presence in the network as well there. The system also supports finding other peers, so we can do UDP broadcasts, so IPv6 multicasts, to find other peers in the local area network to connect to it as a bootstrapping feature. And it provides, of course, basic performance information on how well do we do when we talk to certain other peers right now. Now, one problem if you have all of these ways to communicate is you have to decide which one to pick. So if I can communicate over TCP or UDP or HTTP, I have to sometimes pick one. And I have to allocate resources. I have to decide how much bandwidth am I going to use for my communication with this peer versus with that peer. And of course, the network might not allow me to communicate with Ian with 100 gigabit per second, but maybe it's okay to do this with Tanya because she's at a university in Europe and he is not. Right? So, selecting which peers to communicate to, do we optimize for latency, do we optimize for bandwidth? These decisions are made by the automatic transport selection subsystem, where effectively the applications kind of say, these are our current communication preferences. These are the peers we really would like to talk to, if possible. I'm currently trying to do a voice conversation here, so maybe if you can give me something with lower latency, that would be good. I'm trying to, just send a big message here, but it's not urgent, so maybe give me lots of bandwidth. So the applications can voice these different preferences, and this guy is kind of supposed to try to globally optimize and trade off between the various applications that run at the higher layers. Come on. Okay, so above the transport, we then effectively have to establish secure communication on the first layer. That's the OTR implementation. And basically, it does two things. It does the encryption, and at the same time it says, if there's a peer that doesn't speak the same protocol as the higher level application, so if I have one peer that does whatever voice calls and another peer that doesn't support doing voice calls, they effectively hide that this peer is even in the network from the application point of view. Then we have a very simple service called the host list service, which allows you to bootstrap the system by downloading a list of existing peers from the web. Okay, that's very boring. On the other hand, it's one of these things you do need in practice to bootstrap things. So you have several methods to bootstrap. You can have multicast, you can have broadcast discovery in the LAN, you can have some set of peers you ship with your peer initially, you can manually add peers, but in practice most users, of course, do bootstrap by saying, hey, is there a web server that can give me a list of peers I can start with? And then afterwards, of course, they can gossip and learn about other peers in the network, but you need to have the starting point in practice. Once you have all of that, you kind of get the very basic functionality of, I'm a peer, I have a verified connection to the peer has a certain addresses, and I can, here these are, verified addresses, this peer is available at these addresses over, say, UDP or TCP, and it's currently been picked, the UDP transport to talk with this peer. Right, so it's a simple visualization of what you get from this basic layer. Now, this is not particularly interesting, but if you want to build a peer-to-peer network, this is all you have to do to just start with. Because if you haven't done this, if you haven't done net traversal, if you haven't done peer discovery or any of this stuff, it's a lot of work to just start with. Okay. Then we have a very fun subsystem. It's a network size estimation. Basically, it gives us a log-n of the estimate of the size of the number of peers in the network. So you can just ask how many peers are on the network and tells me an estimate of that. And it does so in a Byzantine fault-tolerant way. So if you have malicious participants, they cannot change the result. It does so in a denial of service impossible way, as in if you are an attacker and you try to use this subsystem to kind of spam the network, take it down, that doesn't work. So that's big problems with previous approaches. So it's extremely cheap, Byzantine fault-tolerant. And if you have a malicious attacker, of course he can run a Sybil attack. If he, buys 10 machines and puts them into the network, well, yes, we will look like we have 10 more peers. Right? That's not really a very strong attack. And the API for the programmer is also very simple. You call this GNUnet Network Size Estimation Connect, give it a callback, and it tells you, our current estimate is 10 peers. Our current estimate is 15 peers. Our current estimate is 320 peers. And it gives you a standard deviation, so you know how close it's likely to be to the real one. The reason why we needed to have this network size estimation, other than being curious about how big our network is, which is one of these questions people always ask, is that for the distributed hash table, it's an important tuning parameter. So distributed hash tables basically store key value pairs over the network. They're being replicated, so if some peer that was storing one of these key value pairs goes out of the network, it's not immediately lost. You can... good way to wake everybody up. Okay. I should have some water. You can have multiple key values stored per key. The basic key difference of this DHT to many other DHTs is that effectively does not make the assumption that every peer can talk to every other peer. All right, so remember we had this underlay on the transport layer. We said this could be a wireless ad hoc network. This could be an IP network where I've got lots of firewalls, lots of restrictions, where the ISP says, oh, you really can't talk to this guy. And the DHT tolerates that. That's the key property that we need here, because we want to use this to establish routes between peers, so we can't assume that routes already exist. The complexity is not that great. So if you look at the overall complexity is square root n log n for lookup, taking order of log n hops, so it's not great for denial of service. I've been told somebody has gotten something that they believe is secure at Polylog, so I'll be very much looking forward for that. But in practice, it's so far for the scales we're talking about is dealing fine. So we did experiments with up to, I think, 100,000 peers, and it was performing just fine, 5, 6 hops. But of course, the question is, once you go internet scale, square root n might still be awkward. So anybody who has better ideas how to do it, demonstrate it. The API in the end is very simple. You have, get, I have a key, find me the value, put, store a key value pair. Now, one of the key things we have is, when you do this, there is this one DHT that's going to be used by many applications. And different applications will have different semantics for what these values are that are being stored in this thing. And the DHT allows you to say, is this value actually correct for this key, for this application? So if you have an application, like we'll see later, the PKI, you might say, okay, I can verify a signature here. Or you might say the value the key has to be the hash of the value. So this kind of, if the application has a particular way what the relationship between key and value has to be like, you can say, dear DHT, here's a method for verifying that this relationship is correct. And that way the DHT will not spread values that are malformed. And that can be key for performance, because if you try to look up a key value pair that should be properly signed so that no malicious person can put in a value, it's important that within the DHT already bad values aren't propagated, as opposed to you at the end getting all of the garbage of somebody spamming a value with a bogus signature, and then you going, oh, this is all garbage. Throw it away, find me the real one. Right? If it's already discarded in the network at the first non-malicious peer, that's an important feature to make sure that bad values don't propagate. Yeah, so then we have, on top of the DHT, we effectively use the DHT to find a path from one peer to any other peer. Effectively, every peer can say, I am here. This is my peer identifier, puts a key, does a put of his key into the DHT. We trace that path. If I do a get on the same path, I have actually a path between the two peers, and can thereby establish an end-to-end encrypted channel. We do this for several times, so we get several paths between the different peers, and then establish one end-to-end association that we use Axolotl to protect the conversation between the two peers. In the end, for the applications, it's very simple. You have kind of like a listen API where you say, okay, I'm waiting for incoming connections here. Please connect to this peer, and then you have send and receive between the two peers. Peers so far, for us, are identified by their public key, but they are not the same as users. So again, we have a peer, which is a set of processes running on a machine, and then that peer might be used by one or more users, where users, again, they might be just pseudonyms, or might, of course, be no users associated with a peer as well. And again, the users are identified by public keys, and you can have many of those, and the identity management effectively just says, okay, this is my set of private keys for my user identities as opposed to my peer identity. Then these identities are used in the public key infrastructure so you can name users, name services. With the GNU name system, it's a decentralized name system where we have secure memorable names, so your names can be structured like in DNS, so you can have, alice.bob.dave.gnu, and that's the delegation chain, and that securely identifies this user. We can have globally unique secure identifiers, similar to what you have in .onion. What is key here is we have query and response privacy, so when you do look up a name, unlike in DNS or DNSSEC, where whenever you do a query, it goes out in the clear, the servers know what you're looking for, everybody can see the reply, and of course, in the case of DNS, even change the reply. Here, we've got effectively private information retrieval except that the confirmation attack is possible. So kind of combining the two of your things. Confirmation attack, if I know what you're looking for, I can say, well, this is exactly the response everybody would get when they look for this user. On the other hand, if I do not know what they're looking for, I know nothing, have private information retrieval for the name lookups. It is interoperable with DNS, so we made sure that you can put standard DNS records into the system, even though, of course, in practice, we will mostly put records that are specific to peer-to-peer applications into it. Again, if you want to use it, it's rather trivial. You connect to the DNS resolver, and then you can do lookups, and you get your results back as they have become available. Here's an example for a little application for your zone management. So, for example, here I have my different zones, my private zone, my master zone here, and in that zone I have labels like in DNS, and I have record types. Here I've put in an A record, an IP address, I have an expiration time, and so you can manage your zones just like you would in DNS, except that you have more record types. When you have keys, you have to possibly say, okay, maybe this key can be compromised or can be lost. So we have a key revocation protocol. Here, unlike other TLS-like key revocation protocols, the overhead only happens if you have to revoke a key. If you have to revoke a key, you have to do a proof of work calculation, so you can't do this too much. And then you flood the network with your revocation certificate. All the peers pretty much instantly learn this key has been revoked. And then there is no delay to check, hey, dear certificate authority, has this key been revoked? No, you already know it has been revoked. So it's an extremely efficient, extremely fast check to see, has this key been revoked? And the cost is really only there if somebody has revoked a key. Otherwise, it's free. Again, the API is rather trivial. You can just say, hey, revoke this key. And you can say, hey, has this key been revoked? So then we have a very generic mechanism in there, which is the set service. With set service, you can think of mathematical sets. And the set service allows you to say, I have two peers. This peer has a set, this other peer has a set. Let me compute the set intersection or the set union. And it effectively, efficiently gives both peers the differences to the desired set union or intersection from the starting sets that the two peers had. One of the things we use the set service for is to build a scalar product service. So here the idea is that we have two private maps. So Alice has a map A to some numbers, Bob has a map B to some numbers, and what we want to calculate is over the intersection of the two maps, the product of the A and B values. The current implementation is very bandwidth efficient. It takes about 100 bytes per element to do the scalar product. The computation time to do this is in milliseconds. And the nice thing is it's a secure multi-party computation, so if you have these two vectors, you only leak the result and what you can derive from the result to the other party. And of course, like any secure multi-party computation, it assumes honest but curious adversary. If one party lies about their scalar vector, the result is garbage. Again, very nice API. You just say, okay, start this computation, here's my vector, or I'm waiting for somebody else to do a computation with, here's my vector, and you get the result back. Currently working on a protocol for secure Byzantine fault-tolerant random peer sampling. Here the idea is I want to get a sequence of random peers in the network. Just give me a random peer in the overall network without using a central service. There's a protocol called Brahms that was published a couple of years ago. And the basic goal here is ultimately to be able to replace something like Tor directory authorities, where you have a well-identified small set of users that if you compromise those, you compromise the security of any system that relies on random peer sampling. So if we can build this in a very decentralized way, that would be a benefit, in my opinion. We are also currently working on a multicast primitive where the idea is I have one user who wants to communicate to a large number of other users to notify them of some important event in a publish-subscribe fashion. And again, the key is here to make sure it's end-to-end encrypted, but that the source, if you have a million other peers to communicate in an end-to-end encrypted way with, you can't afford to do a key exchange with every member, so we have to kind of decentralize the key exchange, building on the fact that we can trust members in the group to not falsely spread the information, because of course they could do that anyway, because they can just decrypt it. So we can ask them to kind of help with the key exchange and key management. Over the multicast, we're building with Psych2 XMPP-like messaging protocol with extensible syntax and semantics. So those familiar with XMPP here, it's more efficient encoding, and it has not just the extensible syntax that you have in XML, but you also have kind of inheritance built in, like from object orientation. So if you refine message types, applications can say, okay, do I understand this refined message type, or do I handle it in a more generic fashion? Using Psych2, we're then building social networking applications, where, again, users can, we have some kind of generic concepts that map to existing social networks. So you have users in the network, so what you would expect. So we call them NIMs because I can have, of course, many identities in our case. We have places where the social interactions happen. This could be like your Twitter channel or your profile or a chat channel. So it's just where the interactions happens. A place has to have a host. That's kind of the source of the multicast tree. It's the guy who controls access. And you have guests who are visiting the places. And then you can enter places, leave places. You can have the host accept guests or refuse entry. As a guest, you can talk to other users. A place can have a history, so you can look at what is the conversation history at a place, and you can inspect kind of the state of the place, which might for a chat be the subject, or for a profile be the image of the owner or whatever. So we're using this generic API where the NIMs and the naming of users uses the GNU name system as a PKI, and we use Psych for communicating the state of the channel and sending the messages out. We believe we have a very generic protocol for building all kinds of social networking applications. So with this, there's a student of mine who is building SecuShare, which is the first social networking application. I asked him to send me a screenshot, but he didn't yet. Okay. Then, in the system, for research purposes, we have built in some basic ability to collect statistics. So you can just say, hey, I have an interesting event, collect this number of peers I'm connected to, collect this number of packets I have received, and you can, of course, plot them then. This becomes more interesting when you look at the testbed infrastructure. So we have the testbed subsystem, which allows you to launch many peers easily. So you can say, I want to launch 100 or 1,000 peers on my computer, or here's the cluster, take these 20 machines, launch 20,000 peers on that cluster, or I have a supercomputer here, please launch 1 million peers on the supercomputer. You give him the resources, you tell, here's the job control, you say, what is the network topology you want? You say, I want, the peers to be connected like this, I want the following additional processes to simulate user activity to run. Here are these statistics that I'm creating with the statistics subsystem, collect them to me in the end so I can have some outcome of my experiment, and then you can launch this and run experiments to see how the network would behave if you had whatever number of peers under whatever scenario you want to evaluate. Then we've built applications using the name system like Conversation, which effectively uses the GNU name system to name users. And we have we use Opus to encode the voice stream, and Cadet to have end-to-end encryption. And then, so here's a little example. You pick who you are. So here I just pick my default ego. I have my address book down here, which is again just like a DNS zone. And then here I would have my information of who is actively calling me, and I can also specify who I want to call. So for example, here I could type in call alice.bob.gnu, click on connect, and then it would establish a phone conversation to that user. Here one thing that is, would be very interesting to maybe, well, it's a question of privacy, to have something like DP5 for presence, because so far we only have a DNS-like, with the GNU name system, lookup of the public key and addressing information of the target user. We can't show you, are these users online right now, because we don't have DP5. Oh, and it still doesn't have ringtones. It's been waiting for 2 years for some guy who said, I have ringtones for you, and I said, send them to me. You never got them. But it's end-to-end encrypted, great public key infrastructure phone application without ringtones. So Okay. Then one of the first applications we had for GNUnet was anonymous file sharing. I don't like the term file sharing anymore. We call it publishing, of course, these days. And publishing is a good thing, sharing is bad, as we have learned from industry. So we break up the files into blocks so we can stream the blocks from multiple sources at the same time. Like in the GNU name system, when you do a query, it's encrypted, so the people who are answering the query, even if they're just routing the request or the response, don't see what you are downloading or transferring. We have a mechanism to kind of track which peers are answering our replies, and if they do answer our replies a lot, then we will prefer answering their questions when they come along. Of course, we support keyword search. We have file metadata available as part of the search results, so you can already have previews or see a bit more than just the file name. You can share a directory and then mount it via Fuse, the file system and user line extension of the Linux kernel. There's APIs to access file sharing. There's command line and GTK GUIs for it. Yeah. More fun stuff for searching. The previous one was just searching with keywords. Here we can search with using regular expressions. So you can say, okay, I have this regular expression. I want to find anybody in the network who has published a regular expression that matches my search string. And effectively, it uses the distributed hash table to look up peers that have published that they are matching this regular expression. The API is rather easy to use. You just say, I have this regular expression that could be found, and search for somebody who has who matches this regular the string. But you have to read up on the regex prefixes before using it. I had a team using it, and they didn't look at the need to prefix the regular expression with an application-specific prefix, which we use so this is this application or that application, and then the performance goes to hell. So read a bit up before you try to use it. We use this regular expression search to, there's two more later. Okay. First, so we have a DNS integration where we can effectively say if you want to use, have an application that still uses DNS, but you want to use the GNU name system for it, we can kind of grab your DNS traffic and modify it on the fly. We use this to implement NAT-PT for IPv6, IPv4 migration. So if you have a machine that says, okay, I'm only on an IPv4 network, but DNS gave me an IPv6 address back and I can't connect to that, we can effectively modify the DNS reply, route the traffic through the GNUnet, and perform NAT-PT for protocol translation. I thought this was, yeah. So here you're running effectively now IP traffic over GNUnet, right? Now you might say, why would I run IP traffic over GNUnet if I have IP below? Well, first of all, you may not have IP below if you're running over Bluetooth or wireless networking, right? And the other thing is with IPv4, IPv6, well, some people only on IPv6 can't talk to IPv4, and some people only on IPv4 can't talk to IPv6. So there's one migration mechanism you can offer this way. Not to mention, in the end, one thing you can, of course, do with this is you can run like Tor hidden services, where you have your machine offering an IP service in the GNUnet, and you route to that IP service over GNUnet. Except for with Tor, you can only do TCP. Here, you can also do UDP and ICMP. Then we've built a Byzantine fault-tolerant consensus protocol. Here, the idea is you have threshold cryptography involved, so you have a certain number of malicious participants you can support. You want to compute the union of the sets of all of the participants at start. So I have, n participants, they have a certain set, and I want to compute the overall union of all of those sets. Unlike other consensus protocols where you compute, a value or a state machine, here we really explicitly focus on set union. We have the usual constraints, you have to not have too many malicious participants. We assume, in terms of communication, partial synchrony, as in we can say there is a bound on how long messages can take over the network. If you don't have those kind of assumptions, synchrony is a bit too strong. No synchrony, and you don't go anywhere anymore. And so then we have Byzantine fault-tolerant consensus. Using that, we can build Kramer-style electronic voting, where we have the usual properties of it. Of course, votes are being counted correctly. So the votes are effectively what you do the set union over. Right? If you have the Byzantine consensus, you have these voting authorities that are supposed to compute the result of the vote. And you first, everybody submits their ballots, and then you have to do the union of all of the ballots to make sure that everybody starts with the same set of ballots to do the secure multi-party computation on. So here, you get correctness, you get secrecy of the vote, you get individual verification, you get universal verification, you get fairness, you get robustness, you do not get coercion resistance. So an adversary could verify that, hey, I asked you to vote for this party and you didn't. Right? So that's what we do not get here. But otherwise, it's a reasonably efficient protocol. If you can, it's not fully decentralized in the sense of course, you still have a set of voting authorities that are going to collect the vote and do the secure multi-party computation, which is typically smaller than the number of users. And most importantly, you still have to have a supervisor. The supervisor is supposed to say, what are you supposed to vote on? Somebody has to decide what's the question we're going to answer in the vote, or in the election, right? And some supervisor mechanism has to be there to decide who is eligible to vote. So those things we didn't decentralize in that sense because that doesn't seem to make too much sense for an election. So then for some of these services we've started to build RESTful APIs. So you can either access them using a C library, using inter-process communication, or using HTTP with JSON. And there are some people who are building effectively identity management solutions for web applications using the RESTful APIs. That's why they did this. So now we're also starting to build a payment system. I should emphasize payment system, not a new currency. We're not trying to do another Bitcoin. In our case, what we want is, it's a bit not so much GNUnet anymore because it's not peer-to-peer. And the key reason is that we want to be able to say income is accounted for. The state can say whenever you receive income, because we believe that the state should be able to tax you on that and be able to say these are illegal uses of payment systems. You're doing, tax evasion, you're doing weapons smuggling, anything like that. And so the receiver of money should not be anonymous. And that kind of requirement means for us that you can't be fully decentralized. On the other hand, when you pay, you should be anonymous. And that's what we're implementing with Thaler. It's based on Tron, but with some improvements. The overall system looks something like this. The various dependency graphs between the various components. So, again, this is simplified. Right? And now you go, oh my goodness, and he said the existing thing was complex. Now I want to give you a little bigger shocker. So this is GNUnet, and if I put this on top of the existing Linux system, GNUnet is here when I do the compilation on an operating system like GNU GIX. These are the dependencies in the graph between the dependencies of what is below us at compile time, and this is what it looks like at runtime. And when we looked at it more closely, it turned out that this distribution didn't actually build all of the optional things. Now, you might say, oh my God, what did you build? It turns out that some of these things are very simple. I think this here might be curl, right? So libraries that are absolutely standard have themselves sometimes really crass dependency graphs, right? So if I just show you the full dependency graph, the problem is usually you don't see that, right? It still exists in the systems we built independent of GNUnet. Okay, future work. There are a couple of work in progresses in there. We want to add onion routing once we have Brahms working. We want to have more asynchronous messaging. I want to add secure auctions, news distribution, timeline construction, collaborative editing, multi-party linear programming, lots of new things that we can build cool applications with. Anyway, to conclude, GNUnet provides some foundations for an alternative network stack. We need more work. SMTP 2.0 isn't there, Tor 2.0 isn't there, Web 3.0 isn't there. And of course, there might be lots of primitives. You might say, oh, this could be a cool thing to have. I would like to have DP5, for example, in there at some point. I have to see exactly how we're going to do this, but this kind of protocol would be interesting to have. And if you're missing something, feel free to help us. The nice thing is the architecture is very modular. As you've seen, all of these things here are really separate processes. You can separately understand them and use them, or replace them if you have something better. So with that, I want to open the floor for questions.
Thank you, Christian. So other questions?
Hi. Have you heard of the Enigma system that's currently being developed by MIT?
No, not yet.
It's built on top of the blockchain. It's not Bitcoin, but it's pretty similar, and they use hierarchical multi-party computations to do linear programming stuff, and it's It looks pretty cool. There isn't a beta, open beta yet, but you might want to look into that.
Okay.
The white paper is available.
I mean, I am familiar with the Ethereum guys who are building something in part similar also on top of a blockchain. So I don't know, I mean, just with the secure multiplayer computers, I don't think that's what the Ethereum guys are doing. But we did find out there are some other projects that share some parts of the stack, and sometimes we steal good ideas from those projects, obviously.
Yeah, Ethereum is completely loose from the Enigma. Enigma is mostly a research project of 2 PhDs in MIT.
Okay.
Any more questions? Only hungry people? Tanya, do you have information about lunch?
All right, so lunch will be served outside. The desserts are in the small room. Proceed towards the bar. There's all the warm dishes. Well, there's some warm dishes at the end. There's lots of sandwiches. We have some labels. We're trying to get them to put more labels, more information on the labels. Vegan so far is noticed. Vegetarian is not really noticed, but well, the vegetarians should at least be happy with the vegan stuff. So please make your way there, and please be back at 2:30. So we're starting at the regular starting time. And please join me in thanking Christian again.